But I'll just give you the background as to how this talk came about. John Kalb asked me to give a talk, and I said I didn't want to. And so he said, okay, we'll expect it next Thursday. You know. So I submitted a talk, and the program committee rejected it, which was fine. It's a lousy talk. But then there was a gap. Somebody canceled, so I was asked to give this talk that was rejected, that I didn't want to give. So I'm honor obliged to give a bad talk now, and I intend to deliver. Last chance, guys. Okay, you asked for it. Let me just ask one question. What's the difference between a mathematical proof and an integer? It turns out there's no difference at all. We'll come back to that later. That's warning number 2. Okay, so what we're going to do is talk a little bit about typelists. They're very old-fashioned, but lots of fun. They kept us highly amused in the late 90s and early 2000s. And we wrote Typelist Meta-Algorithms. And the person who is most guilty of doing this is Andrei Alexandrescu. And they turned out to be quite useful. It's nice to be able to calculate things at compile time about types. We have many more sophisticated ways of doing things now. We have more language features, especially variadic templates really help us to do these compile time type calculations. But we have all these algorithms lying around that do interesting things with types, like partition types, or sort them, or permute them, or get rid of duplicates, or whatever. And so instead of rewriting them all, why don't we just leverage them? And to do this, we're going to use my third, fourth, fifth, second favorite feature in modern C++, template typedefs. I want to use the templated usings to do all the work for me. Using is wonderful. I mean, people underappreciate using. I know about underappreciation. And so using and I get along well because we have a lot in common. But we're very useful, we work very hard, and we're especially good at cleaning up syntax. If anybody's used an enable if with a long string of conditions on it to do some sphene. By the way, I used to pronounce that sphene, and David van der Voorde, who came up with the term, emailed me an MP3 of him pronouncing it correctly. I like to be taken down a peg, but anyway. So basically, we're going to conclude that all sequences are orthogonal, whether they're types or values or templates or anything. And everything is the same. And the only thing that is different in the universe is process. At least that's my conclusion. So what's a typelist? How many people have actually programmed with typelists? Oh, that's nice. OK. Yeah, they're traditional, but we haven't been using them since C++11. But we have all this old typelist code. So a typelist is not really a list. It's a deeply recursive type definition. And it's pretty simple. A typelist is a type followed by a typelist. And we have a null typelist, which is just some selected empty class. And of course, Andrei Alexandrescu is mostly responsible for wasting my time throughout the early 2000s. What can you do with typelists? Well, you usually do a recursive functional calculation on a typelist, and by doing recursive template specialization. And early typelists were hard to work with because compilers were not expecting to be asked to do recursive template specialization. And if you look at the 2003 standard in Annex B, I don't know why it's called Annex B. Why not Appendix B? But anyway, in Annex B, sounds like a bad horror movie. You will find minima maxima. And where Annex B actually says the compiler should be prepared to handle a depth of template instantiation recursion of length 17. So I asked Herb, 17? Herb Sutter, and he said, well, it's the most random number we could think of. So most compilers could handle about 60 or 62 at the time, and then they die horribly. Nowadays, compilers regularly can recurse a couple thousand times or until resource exhaustion or something. But let's look at our first typelist algorithm. Very simple. How do you know how long a typelist is? Well, the length of a typelist is 1 plus the length of the tail. That's easy enough. When do we stop recursion? when we reach a null type list. So if I ask the length of a type list, it'll recursively do template specialization until I reach this complete specialization that will terminate the recursion, and I will recurse out, adding 1 each time to the length of the type list. So this is pretty simple. How do you make a type list? Don't ask. It was really horrible in traditional C++. Now that we have variadic templates, it's a whole lot easier. But I'm still using what's known as a first rest implementation. I think that term comes from Scott Myers, I'm not sure. But it's a very standard way of doing template metaprogramming. It's been subsumed or augmented at least by pattern matching and other things. But it's still very handy. First rest algorithm simply says, do something to the first element and then do the same thing to the rest. And now you're done. So it's a very kind of straightforward way of doing something. So that's what we're doing here, making type lists. I'm not going to bore you by going on into a lot of detail. But this is a very standard pattern. We have a primary template that's declared, but not defined. We have no use of the definition, but we need to define something that we can specialize. And now I'm going to use my second or third favorite feature in modern C++, a templated using, just to make a convenient name for this thing I'm doing. So make type list is a synonym for calling make type list and then extracting the type, so I don't have to write that ever again. And then here's the termination condition. I terminate when I have a null type list, and the rest part is I create a type list by taking a head and prepending that to a type list created from the tail. So this is standard recursive first less manipulation. But obviously, most people have better things to do than this. Not me. So one of the things we used to do is create pretty attractive algorithms for type lists. Like here's a partition that takes a type list, takes a predicate that asks a question about a type, yes or no. So this is like a type trait. And we can just make a type list of some sort. And then we can partition it. I'm going to call partition. I'm going to pass this type. I'm going to pass this predicate. And this is going to return a partitioned sequence of types. What am I partitioning on? Is it a pod? And so string is obviously not going to be in front of double, so string will be over here or something. And this will partition them according to the predicate and return the partitioned sequence of types. This partition actually would also tell you where the partition point was in the types. And this was very useful for generating conference talks. But on occasion, you might actually want to do something. And I wrote this code about 16 or 17 years ago. So it's probably not very high quality because I was only a high school student at the time. All right, just kidding. So I'm not going to defend the code, but I will say that it does indeed appear to work. The code is all available. I'll send you to a website to pick up the code. So what about today? Modern type lists. Modern type lists are much easier. We just have a sequence of types. And this is a very common thing to have. We occasionally will use the variable as it is, or we may actually unwrap the types into a pack so we can do something with the individual types. And we can partition a type sequence, but why bother? Because we can already partition a type list. So why do extra work? So what we can do is let's first see how we can convert a type sequence into a type list. Well, this is pretty easy to do with pattern expansion. So type sequence to type list. I can make the type, I just call make type list with the types. That was pretty easy. And I'm done. And then, of course, we need a using. We don't want to say ts2tl. We want to say type sequence to type list. And so this is just a somewhat syntactic improvement on this. OK. What about type list to type sequence? I want to go back the other way, too. So here's my primary template. I'm going to use a first rest again on this, probably due to lack of imagination. So here's my primary template. Here's my convenience templated using, type list to type sequence. It's now a synonym for the specialization of this template, plus getting rid of this annoying dependent type name. Termination condition. If I have a null type list, the type sequence is correspondingly empty. And then here's my usual case. And there's nothing interesting here except, I don't know why nobody else does this. I feel like I'm doing something that may be illegal in some parts of the Midwest. I'm not sure. But I know, that was unnecessary, wasn't it? I get even worse. A lot of times we have to take a type that contains a parameter pack of interest and unwrap it. So one way to do that is you pass it to a function and let template argument deduction extract the parameter pack for you, and so on. Another way to do that is just to have a primary template. Here I've nested it inside my TL to TS template. I have a primary template that takes some sort of type, and then I have a specialization that will do the unwrapping for me. And this tends to be pretty convenient as well. And of course, if you want to unwrap 5 packs, you can have a quintuply nested class template inside your class template, thereby earning yourself a pink slip. Okay. Okay, now we can go from type lists to type sequences and type sequences to type lists. So now we can do something. Suppose we have a set intersection algorithm on type lists. It does exist. It's in the code that goes with this talk. It's probably correct. I take 2 type lists, I find their intersection, and create a type list that contains that intersection. But what I'd like to do that also with type sequences. So what I'm going to do is create a set intersection for type sequences that lets me call it like this. And of course, this is a compile time call. So I specialize set intersection with 2 type sequences, our modern variadic type name pack sequences, and it computes the intersection, and there we are. So how does it work? It's easy. Next. No, okay. I once gave a talk to a bunch of actual human beings at our town hall, because I had written a website for the town, and I put up a slide like this at one point and asked if there were any questions. And there weren't. I don't know why. Anyway. Does anybody have any? No, I won't ask any personal questions. Do you still talk to people? Yeah. Because we can get rather involved. So if you've been looking at this long enough, this is kind of like, you know how when mathematicians think something's obvious, they say by inspection? By inspection, this solves the problem. Okay, set intersection for type sequences, what are we going to do? We're going to turn our sequences into type lists, send them to set intersection, get the result, and convert it back to a type sequence. That's all. It's just a matter of translation between formats. It's like any other sort of format translation you might do. The nice thing is that we can leverage the set intersection, and we don't have to do any work, and it does produce a correct result. It's as correct as the original set intersection algorithm was. And we could use it like this. Here we have a couple of type sequences. We invoke or specialize set intersection TS with it, and we'll get back a type sequence. Well, that's not too interesting. Yep. In this particular app implementation, no. I tried to be as STL-like as possible. I was being very pretentious for a while back there in the early 2000s where I was going to implement the STL at compile time. Didn't quite work out. But in this, I believe this set intersection, yeah, that's an easy question to answer. I don't know. I think it does remove, maybe. I'll have to look at the algorithm again. Mm-hmm. Yeah, there's an implementation of unique too that you could use as to facilitate this or not. But the unique is STL unique, so it only gets rid of adjacent equal types. But there's a sort, so you can sort the types and then do. This is the period of time in my life where I almost went out of business because I was spending all my time sorting types instead of doing useful work. Well, as always, we looked at Andrei Alexandrescu and we wanted to do something clever. And so one of the things he did is he had a nice facility in his modern C++ design for making an integer look like a type. All you do is here I have a somewhat modernized version of index to type. It takes, isn't this nice? I can say auto. I can not commit to anything. But I want to commit a little bit, so I'm going to make sure that whatever type this is, it's at least integral. Okay. Or else I could just, be old-fashioned and say size t here or something. But the point is this takes an integer type thing and makes it look like a type, because it is a type. So I can create types, so I can convert integers to types, which is nice. And then, once an integer looks like a type, I can use my typelist algorithms on sequences of integers. So index sequences are really important in modern C++ variadic template programming. We use them all the time to select, typically to basically do index parameter packs of types or of arguments or whatever. They're very, very handy. So one of the things we like to do is we create an index sequence of a certain kind. We could have a sequential index sequence. They were starting in C++ 14. We can generate index sequences from 0 to n-1. There's a make index sequence functionality. If you have a lot of free time, you can also generate index sequences of prime numbers and things that are even and things that, whatever. Subway stops on the A train in New York or whatever the sequence of interest is. And so once you have an index sequence, you might want to do something like sort it or partition it or do set intersections with other index sequences. But you don't really feel like writing those algorithms, although they're not too hard if you are using const expr functions. But here we decided to leverage our existing typelist algorithms. So here we're going to convert an index sequence into a type sequence. And it's trivial to do with pattern expansion. All we do is say, I want a type sequence consisting of these types, and I'll use the expansion here. I'll use the index to type facility here in the pattern, and I'm done. And then for convenience, I'm going to have my templated using here. So I can say index sequence to type sequence. And of course, if I want to get back the original index sequence, which I will, I'm going to revert it. I'm saying revert here because this indicates that I can't convert an arbitrary index into a type yet. We'll see about that. So I can revert that back to an index sequence. And with this in place, I can leverage those typelist algorithms for index sequences as well. So at this point, this is just a quick hand-wavy thing to say that we can take a sequence of anything and convert it to anything else. We can take a typelist sequence, convert it to a type sequence. We can take a type sequence and convert it to an index sequence. We can take, as we'll see, a template sequence and convert it into an index sequence for fun and profit. All right, the point is we have a lot of freedom. So all these sequences are equivalent. There's a 1-1 mapping, as we've defined, between each side of each of these sequences. So now that we are there, let's talk about predicates and comparators. So here's our partition again. This takes typelists, it takes a predicate over types. And so when we call it, here's a type list. We'll make a type list, and we want to partition it. We want all these signed types to come first, and then the unsigned to come afterwards. And so this works very well. The predicate asks questions about a type, and then we can call this type list algorithm. Well, if I want to do a partition of an index sequence, I want to ask a question about an index, not a type. So I need to find some way to take a question about an index and turn it into a question about a type. And this is the way we do it. This is one way to do it, or it's the way I did it, in any case. So here is our index predicate. Takes an index and tells me yes or no. I'm going to simply throw this converter. I'm going to use this to specialize a converter, and I'm going to have a nested template that treats the index predicate like a type predicate. So this type predicate will simply evaluate the index predicate and produce a true or false type result. So it's a very quick and dirty conversion of an index predicate to a type predicate. And we could use it like this, but we probably don't want to. So here's an is-odd predicate. It tells me if an index is odd. And I can create the corresponding type predicate by using our converter. So I can convert is-odd, and I can extract this nested template, and that will be my type predicate that corresponds to the index predicate. Painful is a well-chosen word here. You don't want to do this very much. And I'm showing a little bit of kindness, not showing you how to convert a comparator, but it's similar. So here's the thing. We don't want to be wet. We don't want to write everything twice. We want to be dry. So, all right, that joke doesn't fly anymore. So we don't want to repeat ourselves. So instead of doing something like this over and over and over again, we can create converters. So here's a converter that takes a Typelist Meta-Algorithm and takes an index sequence and a predicate on an index and produces a corresponding, and actually produces a partition algorithm for sequences of indexes. So here's, again, another use of using. So partition for index sequences can be created by specializing this with an index sequence, a predicate, and a Typelist Meta-Algorithm. So this works with typelists. Nobody's seen a typelist since 2011. Nevertheless, this will work. I can take an index sequence and a predicate, and I can partition it and get the partitioned result at compile time. How do I write this? It's, of course, yet another use of using. There's a certain beauty to it. So let's see. The template arguments are the index sequence, the predicate, and the Typelist Meta-Algorithm, which is something that takes a type list and a predicate on a type. And we know how to do that. We know how to deal with this. We're going to convert the predicate. We're going to convert the index sequence into a type list. We'll call the Typelist Meta-Algorithm. We'll get the result, and we'll convert it back to an index sequence. So it's actually fairly straightforward. Once you start doing this, it's very addictive, and you'll start trying to convert, your neighbors into some. Okay, so let's. I didn't mean anything unusual with that last statement. So let's use a converter. So here again, we have our partition index sequence. I'm calling my convert algorithm 1 and getting rid of this annoying dependent type name. And now with this in place, here's my index sequence, and I can partition it using an arbitrary predicate on indexes. So I'll partition this so that all the odd indexes come first, and so on. Now, of course, that's not very useful, but we've seen, I gave a tutorial, it seems like ages ago, yesterday, or Sunday, where it was important, we were trying to use, what's the user-defined literal that uses a character parameter pack? Literal operator template, thank you. And we had to actually we had to parse a user-defined literal at compile time. We take a parameter pack of characters, and we would make sure the pack was properly formatted before we agreed to turn it into, in this case, a date. And the way we did that is we actually created an index sequence of the correct structure, extracted characters from the parameter pack, and then confirmed that they were syntactically correct, and then we could calculate. But this idea of manipulating an index sequence at compile time in order to perform some other operation is not uncommon. Here's just another example without going into the, I went into the detail. Without going into the details here, here's a set intersection for index sequences. And once I create it, I can, of course, here I'm making an index interval. This is non-standard. And here's an index sequence, an ad hoc index sequence, and I can find the intersection of these two by using that algorithm. So, a lot of material But the point is, I really don't know why people are not as infatuated with using declarations as I am. Templated using declarations are so useful. Alias templates, or whatever you want to call them, they're remarkably useful. And they're useful in three particular ways. One is half specializing templates. That's nice. You can also make non-templates look like templates temporarily. Sometimes that's important. Somebody wants a template, you don't have one. Okay, I'll make this look like a template. Here you are. Sounds like a used car lot. And to simplify complex type expressions. That's all of us who have been using enable if, concepts will come sometime. But all of us who are using enable if know how complex those enable if spine restrictions can be. And a using declaration is almost required to make code readable by Java programmers and things like that. So the third use is to do complex transformations that are, maybe not pleasant to set up, but make a lot of otherwise complex things very easy. Here's a one-liner that somehow manages to take some sequences of integers, turn them into typelists, run a Typelist Meta-Algorithm, and then convert the result back into integers. And it's very easy to use. So I would like to end with a challenge. Do the same thing for templates. Create template lists, like this one. Here's a template sequence. I just took some type traits. Write something that converts a template sequence to a type sequence. Use that to create a unique algorithm on a template sequence, and then revert it back to a template sequence. And this should be fairly straightforward, maybe. And I have one last question. So what about going the other way? We said at the beginning that there's no difference between a mathematical proof and an integer. Remember Gödel's incompleteness theorem? I don't, but I remember part of it. And it was the part that had me slack-jawed when I first saw it. One of the things Gödel did is he said, okay, let's take a theorem and translate it into an integer. Now let's prove things about the integers. The same things must also hold for the theorems. And then he proved that we didn't understand the universe at all. And then he killed himself, I think. But it's a very, very interesting theorem. But the thing was, I was fascinated by this some time ago, and so I tried to write a Gödel numbering of the C++ type system and didn't quite succeed, but I did generate several thousand lines of code and made everybody else read them because I published it in CUJ. So the thing is, can we convert an arbitrary integer into a type, an arbitrary type into an integer and do index sequence operations on them and then turn it back to a type? Wouldn't it be nice to convert a type to an integer, do some arithmetic on the integer, then convert it back to a type and see what you get? So that's your next challenge, to do a Gödel numbering. Okay, so you can see why the talk was rejected. But I think there have been several useful techniques in here. The unwrapping through a nested specialized class template is something I use all the time. But just an appreciation for the template type def. It's just wonderful addition to modern C++. One of the two things that surprised me. When it was proposed, I said, okay, yeah, fine, great. But it turned to be a very central part of my programming. It's kind of like variable templates. When they introduced variable templates, I thought, don't we have anything else to think about? But it's great. I use them all the time. So some of these features turn out to be very nice. So if you want these slides and the code that accompanies this, you have to go to my wife's campaign site. You may accidentally click on the donate link or not. So far, nobody else has found it. But anyway, any political questions will be answered off camera. And that's all I have to say, except to apologize for what's happened to you. So anyway, you will find the code here. You'll find the slides there. And thank you for coming very much.